your Valentine. You can have two Valentines, phase 1 and 2. Okay. So I'll read through, to acclimatize you to my accents. As you can tell, I'm not from around here. Kernel services. Number 1, during the runtime, a process may call for kernel services. The system service calls are encoded in files, and this is the source code, syscalls.c. And why do I have an extra parentheses? And /.h, okay, that's the prototype file. I'll just do that later. The duty of an OS is to fulfill the request and execute the service code. While doing so, the process is to be suspended and trapped, wait for the service, and then to be resumed. User proc, this function will make requests for 3 OS services. Syswrite, like print hello world. Sysget PID, get its own process ID. And syssleep, sleep for a period of time. To perform a service for the calling process requires the CPU to suspend the execution of the process in order to perform the service code. After, the process may either be resumed or otherwise due to the outcome of the service requested. Parentheses, IOAs, semaphores, resources lacking as the result of the request, etc. So the process may suspend even longer than they would like to, because certain reasons from the service call. Service calls are initiated by the functions coded in the syscalls.c, in which the inline assembly of CPU instructions are embedded. It invokes the kernel via software interrupt event, particularly through the execution of the CPU instruction. This one, the Intel processor had this interrupt INT instruction. Interrupt go to entry 128 in the IDT, interrupt descriptor table. So interrupt descriptor table is the door that shows the direction of the CPU where to go to execute the next instruction. So it was done by timer before. So basically, timer interrupt the CPU through PIC. And CPU will know that's 32. And IDT, this vector table or descriptor table. Some people say, oh, that's the jump vector table. And has the entry 32 is where that has the new address to the code to continue. Okay. Time entry is the code continue. And then we're going to have 128 out of this table, 1256 entries. And so that's really close to the middle. So this will have the code to execute the syscall entry. And this is not quite C code. This is in the entry.s. So that's inherited from the Unix Linux world that have interface code to call the kernel. Okay. It's going to call the kernel code. So this will be a new organization we're going to have. And we're going to separate the 2 entries in the entry.s now. Before we didn't have the separation because we had only one timer entry that does the call to the kernel code directly. Right now, we're going to have 2, and then we're going to have more. So this is the idea when the instruction is being executed by CPU in the software form is actively or voluntarily called interrupt. Okay, so that's not integer, that's interrupt with a vector 128. Hardware trigger the interrupt of 32. That's by the circuit. and execution of CPU instruction embedded in the syscall is going to do this. So then it gets to do this and then call kernel, and then kernel will call the associated service code. Which one? Service code to execute. So there's gonna be a lot of service code to execute, and they are all in the services.c. So this is the main part of your coding task. So that has a lot of service codes, different service codes, including the timer service is here. Okay, that's the first one we know, and then we're going to have other type of service codes, or in function modules, in module functions. All right. So different from handling hardware around such as a timer device, there's no PIC mask to set or IRQ to dismiss for the software services or the kernel service calls. Only the entry 128 IDT will be needed to carry the address of syscall entry. Like how we bootstrap set up the timer entry, we're going to set up a new entry in IDT, but we don't need to program a PIC mask. And at the end of the service code, we don't need to dismiss IRQ like what we did at the timer service. Okay. Timer service, we have the dismiss of the IRQ with this statement. And then start to like doing other things like upcount the time count for the process and compare it against the time limit. Okay. So this one is for hardware, we don't need to, because there's no PIC involved. Okay. There's no PIC involved. There's a CPU. There's no PIC in the middle. So you execute this instruction by fetching them from the memory, the code or user prompt. And the user prompt calls the syscall, which is a subroutine. And that subroutine is kind of like API. Okay, so this is, people say that application programming interface, like a framework, provides certain function method calls for you to use. So that depends on the designer of those API calls. And then that goes into a special service, belongs to proprietary service you installed as a framework library. Okay, so you want to beef up your system with a third-party framework is to introduce these new fancy service calls or library calls. Yeah, and then that's the changing of adding new DLL files in Windows, and adding new shared object files in the Unix Linux runtime library, so that the new method calls can be used in your Java programs or whatnot, and then the people can use those calls. Okay, so those calls are still built upon the same kernel syscalls in the end. Okay, they're just like a new library calls, still built fundamentally by those system service calls that are the existing ones. All right, but then the user install is not the OS install. All right, so okay, and number 3, the kernel service code get PID service. That's the service code. That's the real thing, the meat. Okay. Place the PID run pin in the process traffic ECS register. So the traffic, when it's loaded to the CPU to resume that process, the instruction pointer will execute a statement after this guy, which will retrieve from the EBX register and return it as the PID. So that completes the system service calls. Number 4, the timer entry and syscall entry will be coded in entry.s. And how to separate them will be in the coding hints.txt, coded like this. And then individually, they will be separated. Enable kernel services. So we have services in the service.c. To enable each is to set the interface. So this is the main work of your OS development. So all the magics are actually here, the kernel service code. To call these is from the kernel main code. And then to interface the kernel main code are these entry points. These entry points are small assembly modules. Their addresses are put into the vector tables, the vector table entries. And then the CPU will jump to those entries upon which event. Okay. So when you event, then the table will say jump to there. Okay. So both will, in the end, call the kernel. Kernel will receive a pointer. That's the process frame pointer. And then use that to decide which service to call. We have timer service. We're going to have the get PID service, read service, and write service. Base 2. So these three services are new after the timer service already there in phase 1. And these three services are being called by the software, which is the user process. So this is the user process. It will call to use these three service codes. Not directly, indirectly. Okay. Indirectly through the interrupt 128 in the API. The actual call is this one. And this one will eventually trigger the service code to run, like a timer event. But this is not timer event, this is software switching. Get PID service is to put the running process PID into EBX in the track frame of the current process. So the current process is trapped in the track frame when the EBX changed. When the process loads that track frame back to resume, then the CPU EBX has the running process ID that can be used to be extracted as the function return of the get PID. We'll see the detailed coding of that. But basically, that's what we've been describing. So, number one of the kernel service code. Service code are collected in the service.c/prototype.h based on the service number set in the register EAX by the sys call. This will be examined in the process track frame. The process PCB has a pointer to the track frame. So EBX is actually the location that differentiates which services. So the kernel is going to look at the EAX of the track frame of the current running process, currently frozen in the track frame. Okay. So basically, this is going to prepare a number into EAX. So that number is one of the three different services. And then what number is that? That number is the write service for get PID. Okay. 20 and sleep 120, 162. So one of these three numbers is put into the API call. So there are three different API calls. And then that's the name of the API to call by the user prompt in terms of the code in the user prompt. And there's a sys get PID. There'll be a sys write. Sys get PID will return my PID. And sys write can write a string to stand it out at the length of the string. And then there will be a sleep. Sys sleep can sleep a number of seconds. The period to sleep. So basically, use a process loop and then have the kernel serve, and the API names are here. The fancy framework method names, and then the duty of each one of them is actually putting this number, different number, into the ECS, and then call the interrupt 128. Okay, so when it comes to the kernel can examine the ECS in the traffic that has different number. That different number will have kernel call different service code. If it's 20, call this. If it's 4, call this in the ECS. If it's 162, call this. Okay. All right, so that's a service number in the syscall quick reference. You have 1 is exit, 2 is 4, 3 is read, 4 is write, etc., etc. Okay. So those numbers are in the API call is to put into ECS, and the interrupt 120 is initiated. Once this interrupt occurs, process suspends. Interrupt means it's interrupt itself. Interrupt CPU that's currently running this instruction itself. And then it goes into, the CPU goes into the jump point and go into the kernel, call the service routine, and come back to the end of the kernel is to select a new process to run. It could be the same one, and then load that process to run. Okay. And it could be the same one, and then the process will resume after this. After this, there will be some code to take out the EBX if the call was an API call for get PID, okay, for example. And then I use that EBX to return extra PID. Because why? Because get PID service is going to put the running process into EBX. All right. So I will repeat that again, okay, many times. Hopefully, don't need to be too many times, okay? that's the hard thing to remember. The story is very long. But gradually, it's from the nutshell, then I'll go into the detail, more and more details. All right, so that's the, okay. So that's number 2, get PID. Number 3, the syswrite call sends the kernel with service number syswrite. Number 4, via CPU register ECS. That's in the API call, along with other needed information standard out in the EBX. And then address of a character string is in the ECS. And the length of the string in the EBX. Then interrupt 128 is called. Okay, so there are 3 things besides the service. Besides the service number in EX. 3 more things is the standard out, is the output file number, which is a flat panel, not a flat panel, the VGA memory of the target PC, and the string address and the string length. All right, and then the write service. The write service receives that. You want to do it carefully. The standard out means the character string is to be displayed onto the target PC console via the VGA memory access, where the video address onside the short hex B8000 represents the top left corner. There are 25 rows and 80 columns in that target PC VGA display. Each position is a 2-byte value. Onside short is 2 byte, composed by the ASCII code, the ASCII number of the character to be printed there, plus the mask, video mask. We've been using in the timer lab hex 0x00. You can omit the first 0. And then still 2 bytes. And then for the boldface of black of the character to be displayed. The service will have its VGA pointer, your service code. The right service code will have VGA pointer starting from upper left. But whenever a character is displayed, it will move to the next column, okay, and then so forth, to the next position, basically. And if you represent the next line, the hardware will do that, display onto the next line. Okay. But the position is continuous from this hex B8000. Okay. And on-site show pointer, we did in the timer lab, a +1 is +2 bytes. Okay. Basically, next column is BA002, and then BA004, etc. 2 bytes per column. But if you have a pointer, your pointer increment is increment 2 bytes already. Okay. So you gotta know the difference. Pointer arithmetic. Okay. If you have integer pointer, okay, then pointer starting with some address of x. Whatever x has a value there being pointed to by the p. When p plus plus is p plus equal 1 or p equals e plus 1, and this is going to have an increment of 2 bytes. Okay, 2 bytes. So basically, it becomes x plus 2 by the byte count. All right, but your increment is increment by 1. Plus p, or p plus equal 1, incremented by 1. It's actually changing what p has from the original address +2. I'm sorry, +4. Integer is 4 bytes in the 32-bit integer platform. +4. So if you print that p, it will print something different from the 4 by 4. Okay, by 4. That 4 is a byte size. So that pointer arithmetic, you have a p points to here. Whenever you p plus plus, it points to next 2 bytes, the new position for next character. So you want to display 1 character, increment the pointer by 1. If you calculate by byte number, you want to add 2. Where you have the where you have a x, integer x set to this number. And then you want to move x to the byte position of the next column from the current one, you got to increment it by 2. Okay. And then you give reference x to be written. Okay, so your right service code will have this VGA pointer initially set at top left corner and gets incremented at the display on each character. Increment 1 position, 1 column. As the VGA pointer reaching the bottom right corner, it should wrap back to the top left corner. So then if you download my demo, you run and you let it run until the display cover the whole screen, it will display something like this. If you push N key like 3 times, you have 3 processes to round robin, and each one is a user prompt. So they will display their own PID like this, and then comes down to here, and then the whole screen will be erased, and then it was starting from here. Okay. Maybe it's process 3 at that time. So there will be a erasure. The erasure is actually display every position with a space. Okay, so you have a subroutine erase when the pointer is reaching here. Okay, the pointer initially it was here. Okay, and then the pointer is reaching here. So this is hex B8000. So whenever the P is greater or equal to the position from the beginning be 8,000 plus 25 times 80. When it reaches this. In order to compare this, of course, this is going to be typecast as the unsigned short. Okay. So this is already declared, the P is already declared as the unsigned integer short. Unsigned short. Short is 2 bytes, long is 4 bytes, integer is 4 bytes. And then the unsigned means that it's used like short 2 bytes, but it carries the unsigned value, not its complement signed value. So this is the pointer declared P, and then equals this typecasted. Because this also has the typecasting of this thing inside here. So starting from here, every time you have a P++, and when P is greater equals to this, then the erasure will happen to erase the whole string. To erase the whole string, actually set the pointer back to the start, and then print in the loop space plus the color mask. It breaks the loop when this happens. When it comes down to erase to the bottom right, and then we set the P back to the beginning again and start the normal display service. Okay, for every string, you display every character, one character at a time. But after displaying each character, you gotta check for erasure if that P has come to the bottom, right? Okay. All right, so basically we want to have the cursor display along the 25 times 80 rows. Within that 25 rows times 80 columns. So we're going to have it displayed from the upper left and line by line, top to bottom, column by column, left to right, and then all the way to the end. Okay. Number 5, the sys sleep we're going to make is going to sleep 1/100th of a second as the unit. So the sys sleep call is going to call with the centisecond unit. Not second, but 1/100th of a second. Okay, we call it the centisecond, yeah. 1/100th of a second. Millisecond is 1,000th of a second, yeah. So 1/100th of a second, centisecond. So basically, it means the number of centiseconds. And we're going to use the PID times 50. PID times 50. So PID 1 will sleep for half a second because we're going to have the get PID call in terms of PID. If a process has PID 1, it will sleep for that PID 1 times 50, okay, 30 seconds. If PID is 2, it's going to be 2 times 50, 130 seconds. That equals to 1 second. And then the PID 3, it will be 150, 30 seconds, 1.5 seconds equivalent. Okay. So this 3 is going to be called not with second value, but with centisecond value. All right. And then this is the sleep call from the process viewpoint. Okay, we're given the centisecond as the input argument. And then the sleep service. So when we come to sleep service, the code that is the kernel code being executed in the sleep service by a CPU. This is because the EX is 162 that's being examined right here. Okay. EX, I'll traffic which one it is. It's 24 over 162. So if it's 162, it will call this. That's calling the service.c. And what does this do? This will calculate the wake up time. The wake up time is the current time. Current time. We gotta have a current OS time. Plus the argument sent over. 70 seconds. So this will be the new wake time. The wake up time for the process. The current running process is the one that wants to go to sleep. And OS got to know when to wake it up. So at this moment, it calculates from its own current time, plus the argument sent over to be the wake time. And put this in the PCB of the running process. Okay. So we're going to add the running process with wake time, with a new integer wake time, in order to record this record. So this is the wake time put in the PCB. And then the running process becomes sleep state. We're going to have a new state called sleep. And then the running process becomes -1, meaning that it's not running process anymore. And then at the end of the kernel code, the process scheduler will schedule a new one. And then process loader will load that new one. Okay? All right, but how about waking up? Sleep servers just put the process to sleep and then change the state to sleep. And then the running process is going to be selected by other process. The timer service is the one that needs to wake up because it's counting the current OS time by the timer interrupt count. So the upcount the current OS time. We're going to have current OS current time. This is also a new one to phase 2. Initialized to be 0 at the init kernel data. Okay, so during boot drive is set to 0, and then timer service needs to do additional things. Okay. It's not replaced with this new code. It's going to be added, okay? Boosted, added with new code, which it does also this, including the new functions here. And the second thing to do is to check the processes, look through all the PCB array to look into their state to be sleep, and the wait time equal current OS time. So that means the current OS time has arrived. Their wait time has arrived, which way you say it. So it needs to be waken up. So the process in the sleep state and the wait time equals the current OS time, matches current OS time. Yeah, because the timer service outcome the current OS time. And then the wait time is somewhere originally much bigger in the future. But right now, because the increment of the current OS time, they are matching. That means the process needs to wake up. So we enqueue that PID, which we found from the PCB array. Okay, index is the PCB array is the PID. So that is the PID to be moved from the sleep state to the ready state. That means enqueue that PID into the ready PQ. Okay, and after it's state to ready. Okay. As before, the deliverable is to Voyager via SMB client submit only source files, not any other files generated by CPE159 compiler into your key folder under the folder phase 2. Means placement incurs penalty. There's some review questions after you do this project. Think about it and prepare yourself for the test. let's take a look at the product C. Product C, you take it in completely, replace the old one. CSUS.C, you need to code. I coded partially for you. Okay. So I'll explain these. Product C already coded. But you got to know why it does. Okay. It's not that. It's already coded, and what do you need to explain? Don't explain. Just explain the one that's not coded. That's hacker. Hackers, just tell me the sequence of these buttons. Dun, 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 dun. All right. So this is the idle prop. Idle prop has changed. Okay. Idle prop, basically we don't want it to call any service or have any delay. It needs to occupy the CPU. Okay. Occupy the CPU. And so it's not going to use any service. It has its own pointer to the VGA memory. And this is going to point to the upper left of plus 79 column. You see the syntax here. So it's like, this kind of give you a hint of syntax what you need for the right service. So this will point to the upper left corner if you set it like that. But plus 79, unsigned short star applies this guy. So this guy is being changed to the unsigned short pointer. This is the pointer address. So whenever you have a plus 79, it's actually plus by the byte size of 79 times 2. It's actually 168 bytes. 158 bytes. Okay. But if you do that, you should parentheses this. Okay. If you want to have an integer by calculation first. Calculate a result without changing the nature of this number, this constant. Okay. So that you put in a pair of parentheses. Okay. One pair is enough. You don't want two pairs, 3 pairs, 5 pairs. If you wrap it so many layers of tortillas, it's still burritos, yeah? But it feels safer. Okay. But we didn't wrap it. Oh my gosh, it's not a tortilla, why is it? It's an enchilada. And so here, this one becomes a pointer by nature. So any calculation afterward, 79 actually means 79 times 2. Why is that? Because unsigned short is 2 bytes. So this is 79 times 2 in terms of byte size. That changes P. Okay, P becomes points to here, but this has been typecasted here. So this is going to be dominant type, just like you learn programming say. 5/2 is not 2.5. Oh my gosh, you know. Because 5 is integer. Okay. If you want to get a floating point, then the 5.0 times 2, you want to write it like that. Then you say, why not 5.0 times 2.0? You know that the first number is dominant type. It's going to change to 2, becomes 2.0. Okay. So here the dominant type is being typecast. Okay. So that's why it will move to the upper right corner, which is column 80. Okay. Column 1 is this number, and then plus 79 becomes column 80. You can think about it's column 0, and then plus 79. That's the 80th column. To do what? To display it's a 0. Okay. Idle prop is PID 0. So we want to display 0 like this. If you display your name character, it's that character plus the column map. And then so the reference P will use where P points to put into this value. Okay. ASCII single character is 1 byte, but in C it allows you to use it like a number. So kind of like 8-bit number. And then plus there's two bytes. Okay, so basically it's a number calculation. It's ASCII code 48 plus this. So when it becomes ASCII code 48, it takes into the form of a number. Yeah. So it becomes the star P will be given a 2-byte number because it's unsigned short point. It points to somewhere that can carry unsigned short. So this is the formation of unsigned short. is the ASCII number plus this. Okay. The truncates, if you had some, if you experiment for the experiment C code, outside shore storage, you put larger number, more than the precision of 2 bytes, it will truncate. It will just use the right 2 bytes, the LSB 2 bytes, in the big endian notation. If Intel is a little endian notation, it's actually left 2 bytes. And then the first byte is actually the second byte. Second byte is actually the first byte. But anyway, that's the storage detail in the memory. If you're going to use GDB to trace things, looking into the memory, you got to understand what you're looking at is a little endian byte order. Okay, so sometimes you look at the value of an integer 4 bytes in a 32-bit platform we're using now, like that. Okay, X is given 8. Then you have a GDB. Okay, then you print ampersand X. It will give you an address. It will give you an address as and then you want to print the address, so you print it. The address. You print this place. So it's like a character. You want to print 1 byte. X 001108, and you print 0. Oh my God, where's A? Because A is gonna be this guy plus 3. B, C, D. And then when you print the D, and then you print A. And then you realize the storage, it will, the storage, it doesn't store it like that, it stores it like this, A, 0, 0. So this becomes the first byte, and this, the byte order is in reverse. So within a byte, it's still 8. Okay, but the 32-bit in 4 bytes in the storage memory location is not stored like how you think about the big endian. Like 32-bit represents this decimal 8, and then the first 8 bit is the first byte. Okay, the last byte is not the first byte. Anyway, so all right. So what does this do? This will display 0, and then wait for half a second. If you do this loop here, divided by 2. If this is 1 second loop, like 1.6 million, then it will delay for half a second, because every time this call of the SM in B Intel assembly from the CPU instruction will cause 0.6 microseconds of delay. And then display space, erase it. Erase it and then wait for half a second. So basically you see that 0 will flip, will twinkle at the upper left corner. Okay. So you will see at the beginning run, when you don't push any key, the 0 is going to be here, on and off in the 1 second cycle. Okay, on half a second, off half a second. All right, that shows that idle price running. Okay, that indicates idle price running. So we don't need to, but we show it at least. You know the idle price running. If the traffic is not loaded right, you didn't dismiss the timer IRQ, then the idle price is not even running because there's no timer interrupt. Wait a minute, what am I saying? The idle price is running, but there's no time interrupt. Maybe there's some other problem. So it's better that this will indicate at least idle price is running. And then you push N key, the user price created, The user product looks like this. You have my PID. We can call the syscall get PID, return my PID. And you have the centisecond to calculate by the my PID times 50. And then you have a string that has the 3 spaces, NTI, 3 spaces. And character string without a dimension here. So that's 3 spaces. And the actual string length is 3. The actual size is 4 because the null termination is added by the compiler. So every string, the length of the string is, in this case, 3, but the size has a null termination included as part of the string. So the size of such a 3-character string is actually 4 bytes. Okay, and then the string length, that's a built-in C function. It will know from the beginning to the null, calculate this is 3. Okay, 3 character valid characters. Okay. So whenever you have any double quoted thing inside the C program, the compiler will automatically add a pen with a null, with a ASCII 0 byte. Okay. My PID and calculate 30 seconds. The 2 PID digits, maximum 2, is being put into a string like this. Okay, the ASCII character 0 plus the how many tens. You know? If your PID is less than 10, it will have a 0 by the division here. If it's 19, 18, 11, etc., it will have a 1. It will increment this by 1. It will come to the ASCII code for letter 1, okay, 49. ASCII 0 is 48. So this will may be given 0, maybe given 1. So if it's given 0, it doesn't change this. If it's given 1, it's going to advance to the next character in the ASCII table, become 48, 49. 49 is the character 1. And here, do the same with this mod 10. So that's the right digit of the 2-digit PID. The right digit can be 1 through 9. And could be 0 to 1 is PID 10. So that's gonna make the second character, the character represent the PID. Okay. So we can display something like 0, 1, 0, 1. And then the space, okay, we're going to have another character that's even from the initialization space. So that would be display 2 characters in the space. So we're going to send it to display by the sysprint. Syswrite. Syswrite standard out is the constant, define the kernel constants. This is number 1. And then the string is the address of the string, char star. And then this is the length, 3. Which is hard-coded here. And then the sys sleep will sleep for the centisecond, calculated here. And it loops. Okay, we loop with these 2 calls. All right. So how do you write the syscall.c? All right. So this is the mystery. This is the API code, and you can see it's not really the service code. It doesn't do too much. We want to go into the kernel to do the service there. Okay. So the process, I use a proc calls the get PID like this. And this is the integer return function, or PID type return function in the real OS. They type it outside short. Yeah, they can use a 2-byte outside short for the PID type. But we just keep it simple. We call it integer PID. Okay, and return the integer. So the ASN embedded the inline assembly looks like this. That's in the string double quoted. We have 3 statements. Separate the 3 statements with 2 semicolons. Okay. So here the syntax you got to pay attention. All right. So one of the representatives of your team, pay attention, please. Okay. So this is double quoted string containing 3 CPU instructions separated by 2 semicolons. And then this is move L, not 1, it is L. So this is 1, this is L. So this is percentage, this is dollar sign, this is double percentage symbols. And so the syntax is very gnarly, okay, very gnarly. How do you spell gnarly?
Narly.
That's one way to spell it.
How do you spell it?
G.
Or is yeah.
That's a G. I thought it was a K. So people say thank you in China. They say 谢谢, 谢谢, and 谢谢. You say you're welcome. You just say nali nali. Nali nali in Mandarin means where. Where means yes, I don't mention it. No problem. So you say nali nali. And so it kind of makes total sense, right?
Mm-hmm.
One guy says shay shay, in English it's kind of like sh something, and then the so it's nali nali. Okay. So the syntax is very gnarly. Okay, so that's what I'm trying to say. It's very messy. And after the double quoted assembly commands, CPU commands, you have these 3 lines that started with a colon, and they are the output, input, and register list. Output from where? From this double quoted area. Input to this double quoted area. And then the registers being used inside the double quote. Okay. So that is required. Is that why? Because the register is gonna be pushed and pop if they are being used inside here. So the process can retain the original value of the register if they are properly pushed and pop back. So the compiler will actually compile into the code that pushes the EX and EBX and then execute these 3 instructions. After will pop EBX and pop EX. Okay, that will be a total compilation result. All right, so %1 means in the output input line, you count the number of arguments in parentheses. Okay, this is %0, this is %1. You start from %0, you start from 0. So PID is %0. Use as output the syntax in the double quote format is equal G. Okay, equal G. Equal G, meaning that the PID will be written as the output when you have an output statement here. Move L, register EBX to this guy, PID. Okay. %0 means this. %1 means next one, CSC PID. CSC PID is the constant 20, constant 20. The constant 20 will be put into EX as the service number. And this one, we didn't use any, we could, but this one's fixed, 128, interrupt 128. That's a system call. Okay. This is $sign for literal, okay, for immediate. So don't type these wrong. Most people type these symbols wrong. If they are wrong the whole semester, they still couldn't figure out why it crashes. Segmentation. So the percentage and the symbol here, the registers have 2 percentage symbols, and the literal is a $sign. Don't get that wrong. The %1, %0 has 1% symbol. And the EX, EBX are the 2 registers quoted each separate with comma. All right, so then the function returns here after the call. So what does the call mean? Call means that you put number 4 into, number 20 into EX. That's the get PID service. And then call the syscall interrupt. and then that will interrupt the process runtime of this code right here, which is user prompt. So user prompt will be frozen into traffic in the event of the interrupt service. All right, 128 is this one here. So hardware will push the EFL CSEIP. So that is the beginning of the traffic. So when interrupt, something happens. The hardware, just like timer interrupt. Timer event. Hardware pushes EFL, CS, EIP. Okay. And then that's the first three things in the traffic. And then followed by the interrupt number. This is software. And then the register. The register we're going to have EAX, ECX, EPX, EPX, and then 4 more. So this is the traffic type. Okay. So then the hardware will disable the interrupt flag. And what does that mean? That means the CPU will stop recognize any other interrupt until you finish the service. So at this point, the CPU will not handle any new interrupt. It's going into the interrupt handling. Okay. And then the jump to IDT 128 instruction supplies that. Jump to IDT 128. And the 128 is the software that started the code here. The code here will push 128 and then jump to enter kernel. And the kernel is the common routine of the original timer entry code. Timer entry will push it 32 instead. We'll jump to the enter kernel. And enter kernel is the original code that push A and switch stack pointer to kernel stack and push the ESP there and then call CNAME kernel. Okay, from phase 1. I'm sharing kernel pico entry.s. Okay. So this is originally timer entry because originally we're going to the kernel the same way. Only timer triggers this to go into kernel. But then we're going to change that. The timer entry is going to push 32. That's a timer constant. And then jump to enter kernel routine that contains these. The enter kernel routine is called by timer entry after push 32, and also called by syscall entry after push 128. And those two numbers will differentiate in the kernel function. What happened that the kernel function starts? Is either this guy or this guy, right? That calls the enter kernel. Inside the enter kernel, if it's 128, it checks further. EX is one of these three numbers, and then call the service subroutine in the service.c. Okay. So enter kernel is the same as here. Push A and copy ESP to ECX, CLD, clear direction flag in the EFL. I guess I have two or two here. It doesn't need to be, this one doesn't need to be. And then and then you move, this is the code. Move the hexadecimal 10 into EX to prime the DS and ES. A data segment select. They need to have these numbers. And then load the kernel stack into ESP. So we switch the stack pointer. Okay, it was after push A. Yeah. After push A, it completes the traffic. All right. So the stack pointer is right here. This is upside down, okay, in the memory, in the DRAM. And then that is the place of the traffic or the process just stop. Okay. And then we copy to ECX and then we push to the kernel stack. And we clear the direction flag and call the kernel function C code. Okay, so we change the stack pointer here to the kernel stack plus AK. So the kernel stack starting byte 0, we point the stack pointer to the end of the kernel stack AK. So the stack pointer can push down and pop up. So this is the direction of the stack operation is different from the instruction. Program counter from the bottom towards the high memory to fetch instruction. Okay. So this is 1 plus AK. That's the kernel stack size. Okay. Okay, does that make sense? You gotta study, okay? If you don't study, I cannot do the study during the class for you. So when I was a student, here, the rule is everybody does the same thing. You take note, you take audio, you study the books first before you come to class. So afterward, you can review it. The material in the lecture and study the new ones. It's not one pass. You got to like several passes to study over and over to understand deeper and deeper, more thoroughly. Make sense? Yeah. You said forget about that. Who has time to do that? And so you gotta invent the blue pill. So you can take the blue pill and then you can understand whatever it says in the book. Or in the video, we have a book I put it underneath your pillow. When you go to sleep, if you ever have time to do that, and then the book will go into your dream. And then you understand everything, yeah. At that time, everybody has that. So you don't have the edge anymore. You don't have the advantage anymore. What are you gonna do? So we're in the catch-22 in the technology development era. You want to develop a technology that you put an egg in the microwave and the roast chicken come out. You want to push this button and then $1,000 comes out. Yeah, it would be nice to do that. Once you achieve that, what's next? Because everybody's going to have one. The chicken becomes like, nobody wants chicken anymore. Now people want to invent the cow come out, and then the button will be like $1 million come out, and then everybody has one. Then the $1 million becomes worthless. It doesn't even worth the paper it prints out.
And then Bitcoin goes up.
Yeah, and then Bitcoin is everybody want. We want that Bitcoin because we cannot get it. So it's a paradox. Human nature is a paradox. The paradox is right here. You are studying computer technology. You want to invent things to make things convenient. But once they are convenient, everybody's like, it's boring. We want to have some challenges. Like climb the mountain barehanded. So why do we need to climb a mountain? The chopper can take you to the top of the mountain. Yeah. But the journey is the reward, like they say, the cliche. So what am I saying? I'm saying the paradox is this: you are only happy when you get the things you can never get. All right, then that means you can never be happy. You got the things you could never get. You're happy now, but then once you have it, you're not happy anymore. You still want to dream of the things you cannot get. Yeah, but that's human nature. That's why we see every time we see a mountain, see the horizon in the ocean. You know, we want to get to the next island across the ocean. You know, we want to climb up to the top of the mountain. There's nothing there, just bare rock and frozen to death. You know, want to come down to Starbucks. You know, use the Wi-Fi and have hot coffee. Who wants to be on top of the mountain? Or you can take a selfie and bring it back, you know. But selfie is only meaningful, you know, when you put it on the internet. That means you're not happy by yourself. You got to have all the other people acknowledge you to be happy. But is that real happiness? Yeah. Open question. There's no real good answer. You won't be on the test. Don't worry about it. Okay. So your mental challenge, okay? So understand this, and then you understand, it is so simple, you know, 159 is so simple. Why do people feel it's complicated? Because you conquer that slope, you come to the top of that mountain, okay? Does that make sense? And because from that little hill, you will see even bigger mountain. Because then you realize, oh my gosh, there are a lot more things that can be done here. Okay, so that's the, so that's phase one. Remember, that's what I meant, that the original phase one timer entry code becomes the enter kernel common routine. Okay. So after knowing this syntax, how do you do the other two? Let's say the small one that says sleep, getting an argument which means the number of hundreds of seconds to sleep. The SM is blank. Oh my gosh, what am I going to fill out here? So you got to call the interrupt 128, but you got to first put this into a register and the service number into a register. Two things. Okay, we got to prep two things before we call 128. And there's no output. So the first line here is empty, okay? And the second line here, you have something, which is this thing needs to be put into EBX. And then the service number put into EX, because that's the protocol. That's the protocol kernel is going to check EX. Okay, so don't put the sleep number of seconds, 70 seconds in EX. It's this, says sleep. Okay, says sleep 162. Need to be put into the EX as the service number. And then EBX will have the number of 70 seconds to sleep. You want to put it into EBX before you call the 128. Does that make sense? Okay. So you will have to understand deeper now in order to make new things. You know, it's just like, okay, here's a template. But you gotta understand deeper to make that other things. Here is that we move something into EX, that is the service number, says get PID. And then we're going to call interrupt. Okay. But if you want to move another one, you want to move into EBX before you call interrupt. And the interrupt is called. If there's something more after the interrupt call, we are not done yet, okay? So that means that we need to take something out after the interrupt. After interrupt, EBX has the number PID needs to be taken out, move to %0, and then as the function return. Okay. So this parentheses PID is a local variable that can be referenced by the inline assembly as %0, and then that's how the PID gets to be filled out by the doing of this guy. Okay. And how does EBX has the PID? Is because interrupt 128 goes all the way to the get PID service. And what it does is it puts the routing process into EBX. Okay. So what does it do? It doesn't do much. It just do the traffic EBX equal round trip. This is the current running process traffic, EBS equals round trip. And that's all it needs to do. And then the traffic is loaded, and then we come back here, then the EBX will have the running process ID, which is this current running process ID. And then it will be put into this local variable and return. Okay, so that's the template, the first example. You gotta understand how it works. So you can do the same thing with, again, the sleep. Sleep is not a void thing, you know. Get PID is a void thing and then return the integer. Sleep is a void return, but it will have an argument to send to the kernel, telling kernel how many centiseconds this process requests to sleep. Okay. So we're gonna put that into somewhere in the register, CPU, in the EBX. EX is reserved for the sys sleep, the service type. Okay. In order for this kernel to differentiate from the EX. Okay, so it will by default, the prototype, the protocol is looking at EX on the traffic, knowing which service to call. So we're gonna put this into EX. Therefore, we put 20-second in other things, EBX or ECX, okay, or other common registers. And then the service code needs to comply to that. The sys service will know the wait time is current always time plus the 20 seconds set in the EBX. Yeah? So we got syscall does that. Here you got to match that. Right? So the syscall put into this drawer EBX, and this guy, you know, okay, I'm going to search ECS drawer. You know, you were looking at the wrong value. Well, you want this 70-second sleep for 2 million 70-second. Okay. So that total wrong value in the ECX. Does that make sense? So you got to have the two sides understood. They are linked by this protocol. Okay. You're not the designer. You got to design it correctly. So the syscall has something to do with the service call inside the kernel. So you got to have this comply to that. And then otherwise, this given to the process developer, app developer, they will be calling incorrectly. You know, over here, it's not. But usually this is the install of the framework service code, user install. So it will match the API supplied by the framework designer, which is you. You design the two parts. You should got them organized right. And then many times the bad quality of framework software you install, that they are not doing it right. They call the wrong number, and the register totally using the wrong one. Havoc is going to happen. Okay. All right. So what about the write? The write has more things to send, not just one. But follow the same suit, and then you know that the EAX is occupied by the service call. Says write number 4 is going to put into EAX. And then EBX, ECX, EBX, for instance, following that ABCD notation, we got to put into the file number, the char star, and the length integer. Okay, so we got to put into EBS, ECS, EBX, and before we call 128, but there's no output needed. It's a for return function. So interrupt 128 is the last statement. To change the register, affect the register list is ES, EBS, ECS, EBX. And for this one, it's just ES and EBX. Okay. Make sense?
Mm-hmm.
All right, so that's the idea. And the coding hints starts. You need more constants? You need new constants? We need a syscall 128 standard out. That's the output of the console 1. These numbers represent file numbers like standard in, standard out, standard error. And then this is a service code. Syswrite 4, get PID 20, sleep 162. I got these numbers from the syscall service reference, quick reference. That's universal standard. And then the number 2, add new kernel data elements. we have wait time to add in the PCB, so we can calculate the wait time. And then we have a sleep state to add a new state, so when the process is called sleep, it moves to the sleep state. The triframe, like I listed there, this is the triframe listing, and then we're gonna build a triframe when we create a process. But we're not going to have anything here. We're going to have just the thing we need to fill out. The process runs when the interrupt occurs, either by timer or by the syscall. Hardware will push these three things. And then the entry point will push this thing, either 32 or 128. Right now, we only have two types. And then the push A is going to push these 8 different registers. The space are reserved. The spaces are reserved already. Okay, let's take a break. I forgot to take a break. Sorry about that. Kernel data. The PCB needs to have a wait time to accommodate the sleep request. So there's a state that called sleep added besides the fail, ready, run, the 3 different states. And this is the new triframe. New triframe. The real difference is this one. This one added inside the triframe. We can put it at last, but this one is fine. Put it here. So this putting here is right after the hardware pushes the hardware pushes there. We can jump to the entry. So the entry, either this or this. This or this can push the interrupt number. The interrupt number follows the pushes on EFL, CS, EIP. So the process runtime. When it's first created, the triframe is created. And inside the triframe, the most important thing is the EIP points to the user process code. So this is user process stack, runtime stack. So basically, the stack pointer needs to be pointed to here in order to pop the triframe into the register. So the CPU has EIP and has the stack pointer ESP. So these 2 pointers are important to understand. So we want the ESP to be set here. And that's why we call the process loader during the runtime of the boost drive and at the end of the kernel, where the address of this one. So that's the PCB run pin. So that's a run pin. That's a traffic pointer. And this being set during the creation of the process to point to here. So we give that to the stack pointer. So CPU stack pointer points to this place. And what I'm drawing here is that the tracker inside has an EIP value that's set during the process creation, pointing to the user prop. The idle prop will have the tracker created pointed to idle prop. So that's boost drive creation. EIP will be pointed here. If that's not the user prop, it's idle prop. User prop runtime has the runtime stack has the traffic built with the EIP points to user prop. So the CPU when loads this traffic will have this value override EIP and point to the code here. The stack pointer the process loader will set the stack pointer to this point here to be the get address. That's all. Okay. So then it will start to pop what's in the traffic. Okay. But you need to skip the interrupt number, which is not part of the registers in the CPU. And then IRA pop the EIP, CS, EFL. In reverse of the push, when the interrupt occurs, push EFL, CS, EIP. So interrupt return is actually used for the first time the process is loaded, process traffic loaded. That's if the process is resuming an interrupt. Okay. Even when the process first loaded. So this is the idea to be explained again several times. So this is what you know from the phase one and then extended from time lab. Okay, so the stack pointer can start from the whole runtime stack. After the popping of this, it can override the traffic to run the code here. The code here has a loop besides the initial thing. That will translate into CPU instruction that may use a push instruction. So that is going to override this initial traffic. The initial traffic doesn't need to be kept, but once it's loaded in the CPU, it's going to be as the scratch space. So that's the scratch space from that stack. And then the event occurs. So like this loop here calls the interrupt 128 or timer event. Either it's because the timer event interrupt this loop 100 times a second during the execution of the only two statements in the loop. One is the write statement, says write. One is the says see. Get PID was called outside the loop. You can also have it inside here, but we just have it outside to get the PID once to put into a my PID variable to repeat use that. Or whenever you need that, you just put that inside the loop. Copy PID times 50 to be the argument of the says see. So the loop here also has the possibility not by the interrupt of the timer, but also by the API of the syscall interrupt 128. So either this or this will cause the interrupt, will cause the starting of this. All right, so at that time, the stack pointer is not on top. The stack pointer can be anywhere. So the new traffic build starting from there is going to build from here. And then the stack pointer is gonna be here. And then enter kernel, the last statement is to have this given to the kernel. Okay, given to the kernel. So we're going to have this pass to the kernel. Okay, so this kernel can use it. So this process stack, okay, so this is the traffic build. Traffic build is at the time how we initialize from here, jump to the IDT 128. And IDT 128 is going to push the 128 and then jump to the enter kernel. And the kernel is the same code of the original timer entry. If it's timer interrupt, it's going to push to 32 because that's coded in the timer entry. All right, so push A. Okay. So the hardware pushes the EFL, CSEIP, and then the interrupt number is pushed, either 32 or 128, and then the push A is going to push the rest, EX, ECX, da da da. Okay. So this stack pointer is right here after the traffic is completed. Okay. The hardware pushes the first three things, and then we switch the CPU to jump to the IDT 128. 128 is syscall entry in the entry.s. Okay. So it pushes 128 and then jump to at the kernel. Kernel is the phase 1 original timer entry code. Okay. But what does it do? It will copy ESP to ECX and then set the ESP to kernel stack plus AK that becomes the top of kernel stack. And then push the ECX there. And then clear the direction flag in the EFL, and then prepare to call kernel cname, C function name kernel. Okay, so the kernel function in C code, the ECS becomes the argument, because all the arguments are actually in the stack. So we switch the ESP to kernel stack and push it there. Just like how this is done in reverse. When a C code is called like that, but prod loader is not a C code, it's called the entry.s and then assembly code. And you will get the argument given in the process stack, okay, right above the stack pointer. So here is the other way around. When we have the assembly code push something and the stack pointer move underneath. So here, when this starts to run, it's right above the stack pointer is the argument, okay? This is all done by compilers, okay? Our curriculum is missing compiler construction, so this part is totally mystery to you. And this is why I always advocate CSC159 needs to know that main routine, subroutine call is this relationship. The argument is passed like this, okay? So no matter if you look at a high-level language code like C or low-level language assembly code, why are they doing all these stack pointer thing, around the stack pointer? Then you understand that's how your program runs. All right, so that hasn't been changed for many years because you didn't change it. Because why didn't you change it? Because nobody knew that's how it works. So why nobody knew how it works? Nobody studied this type of thing. So what do you study? Guessing password, of course. All right. So once you know this is called flat memory model runtime. It's very primitive, very crude, okay? But we haven't changed that. Intel processor use this, like many processors, different platform. For certain processors, they do not use it. They have dedicated register to pass argument that get the return values, okay? Like the ARM, like the MIPS. Okay? So they try to change this convention, this very crude, primitive, and very convoluted convention about the runtime of the process. Okay, so that's the idea, so the kernel is called given the argument. So the argument gives the magic. The argument is the traffic pointer. And this traffic pointer can point to know what interrupt number has been pushed. So the round number pushed is either 32 or 28, depends on what type of interaction occurred. Okay. The ground number is either this or that. So here we can differentiate. We're going to have more type. Right now it's only 2 types. So if it's 32, then they call the timer service. And if it's 128, call the syscall service. And the rest code is the same as before. Get a key, N key or B key. And then call UProcess service or breakpoint. And then the process loader, okay. The process schedule. And then the process load. Okay, loader given the argument, that's the tracking address for the selected process selected by the process scheduler to load that tracking to run. And that's the end of the kernel. Okay, so then branch out to timer service. You know how that works. But we need to beef it up with the wake up of the process as new part of the code into the timer service. And then the syscall service is going to check the ECS. Okay. So we prefer to give it the same pointer, okay, of this P here. So we can help a little bit in the code here by not a void argument, but by the same argument passed into this one. So this syscall service can check the ECS and then call one of the 3 different services. And that's the get PID service. So get PID service needs to do is to put the run pit into the ECS of the traffic, currently pointed to by that P passed over. So what you can do is actually give the ampersand of that ECS, like an integer pointer. So the receiving get PID service call can do it really easily. Let's avoid the get PID service. What do you think this is? Yeah. How do you call this argument?
Represent P equal to EBX.
What type is it? So this is the passing over. So you define this code, so how do you define it? All right. You got to boost your C programming skill, okay? If you pass the address of the integer, if you declare it in X, it calls subroutine ampersand X. So why is the subroutine defines in the argument passed over? So the main routine has an integer X and call the subroutine with the ampersand X. So the subroutine, how do you write this? What type is it? Receive argument. How do you write?
Asterisk x.
Huh?
Or int asterisk x. Just guess.
So how do you write it? So use your pen, put it in your hand and write it. What do you write? On the keyboard, what do you type the first key?
Star I.
Huh? Star I. Huh?
That's what I was doing.
It's a cross. You know, this is our civilization is in crisis now. You cannot write this out? Right.
Would it be int star x?
Int star x, okay, integer pointer. It doesn't need to be x, it could be called a. Right?
Yeah.
But if you want to use once passed over to put wrong PID into it, how do you do it? You need to pass the wrong PID. Then what's the code here? So what's this one line code? All right, I'll leave that for you to figure out. Just go to the hacker site, you know, and say a quarter. Anybody can tell me this. Okay. All right. So anyway, so this can help like that. All right. So if you don't know how to help like that, you don't worry about it. You just code it without argument. All right. So basically, if the EAX is 20, we call this one. If it's 162, we call sleep. Okay. Sleep service. If it's the 4, we call it the write service. All right, you got to suggest, you know, like what's going on with our curriculum. We don't teach C. That's the most important language with the CPE, computer engineering. Because the third fight, you know, they wanted to do 1520 Java program. Because that's the money. Okay, the enrollment number. So it has, you know, no use at all for, you know, most of the CP major, not too much use. That leads you to find jobs like Java programming. That's not CPE job, because like MIS or IT. All right. Anyway, so that's you want to control electronics, you got to use C. You know, like probably mentioned before. If not, then you will see the reason is because all the electronics want to have optimized the small footprints of the language model, having been able to control things directly, like pointers. All the devices are memory mapped, so you rewrite memory is to be control devices. And the inline assembly program is embedded into GCC for the C program to control CPU. But you can control the CPU registers. You can rewrite CPU registers, you can rewrite memory locations, and that's why people use C. Okay. And then no matter how great that Java is, Python, Ruby, and whatnot, they don't do this. You know, they are not tools to do inside construction of a building. You know, take down the building, do the wiring and things. You cannot do those by other languages. Okay, so you know, well, people don't understand that. You know, they will advocate Java-oriented programming is the future. but still Java takes the back seat. C takes the, the driver's seat. It's strange. To me, that was strange too. 1995, Java having all the potential and promises to replace C, but it never did. Because it's a different tool. It can never replace the C because of this. Okay, anyway, so does that make sense? So you have three service functions need to code it in the service.c besides this one. Okay, so it's called service. So you have four functions in the services.c. Okay. So this is kind of the header and differentiate what subroutines from the EX pointed to by the pointer passed over the traffic pointer. So that can further lead to know which service to call, which service. All right, so knowing which service to call, the little adjustment in the prod loader is this. So we got to skip the interrupt number 4 bytes when we pop the traffic. Okay, when we pop the traffic, as you can see, we have the traffic build. Then we need to pop A and skip 4 bytes. Okay, the interrupt number is not poppable. If you don't skip this, you pop this. If you IRED here, then the interrupt number becomes EIP. Then all hell breaks loose because that's not the address for instruction. So you got to skip 4. Skipping 4 means you got to advance the stack pointer by 4 bytes. And then come to point to EIP, and then IRED will pop EIP CSEFL. Okay, so that's why it's written like this. Prod loader will get the argument to change the stack pointer to point to the process frame of traffic of that process selected by the prod scheduler sent to the prod loader, and this got to skip, and then skip the prod number, and then the IRED will pop the EIP, CS, and EFL. Then the original interrupt mode is return, because that's before the CLI occurred by hardware. This EFL was created when the process was created, given the EFL the default interrupt value plus enable the interrupt. Okay. And then the EIP is set to the function. And then the runs interrupt occurs. The EFL in the CPU still has that interrupt enable being pushed into the traffic. When it pops back, it will enable interrupt again. Okay. But during the hardware will disable the interrupt flag. So does that make sense? So when the kernel switches to serve a interrupt, either by timer or system service call, the kernel will start to ignore interrupt until it's done. Then the process frame pop back that enable the interrupt again, because that's the original EFL. Does that make sense? Yeah. So the timer interrupt is like, oh, wow, I got to go to the bathroom. The timer interrupt. Yeah, go in the bathroom, sit down. And interrupt mode off. At that point, yeah, until you are done, then you resume interruptible. Meanwhile, no matter what, the doorbell rings, ding dong, the pizza man is here. I'm sorry, I'm not interruptible, you know. So that's the nature of this OS. It's a single level interrupt. What about higher priority interrupt? That will be a real-time kernel. Real-time kernel that will accept interrupt even it's in the interrupt service. Okay. It will still accept interrupt and then push everything into the kernel own stack and then start the kernel in a new stack. So this is stackable kernel. is real time. Okay. Real time system is the one that we need to have autonomous vehicle, to have a self-driving car, or you can forget about self-driving car. Nobody understands the basic idea like this. They still want to make self-driving car. They will know it's gonna be a big disaster, time bomb. And that's why Google been saying that how many years already? More than 10 years, 20 years, still saying self-driving car. I say, we need to still say it 30 years maybe in order to realize you got to revamp the whole system. So gradually they understand, you got to have something like LiDAR, visual radar, and then it got to be real time like the military system, and the real time has got to be so concise and so confined. Your kernel must be so fast and real time interruptible, nested interruptible, stackable kernel, and then the whole control system, even software is going to be totally different, hardware wise too, because right now it's a single interrupt level hardware. Does that make sense?
Mm-hmm.
You say, can you illustrate? I'll try. You think program players can illustrate this? Here it is, the windows to the future.
Whoa.
You see, this delay is not very acceptable. Yeah, from one hand to the next. We don't need to look into more levels.
That's great.
In the speed of 60 miles an hour, okay, you have this delay. Disaster is at hand. Even that we are inside the same room. Yeah, the Wi-Fi. So that's the. You see, this is can I even tell the sequence anymore? Puppy show. Yeah. So this is the fundamental problem first. Our system cannot control things real time. Okay. If you want to use your laptop to do senior project like real time control, good luck with that. Well, you can do very slow things, maybe a bicycle. I think we're going to have self-driving bicycle first, okay? Otherwise, self-texting phone first to leave you driving. The phone text for you. That would probably safer. So you never played this before?
We don't have a projector at home.
You just have two laptops facing each other. Yeah. And, why if you go to the fairground, they have the mirror thing. But the mirror is real time. It is the light speed, so you don't really see the delay. But the electronic delay is really too pronounced. So that's the thing. Yeah. So that's what they realized immediately. Oh my gosh, we gotta revamp the whole hardware software system. There's no way that we can have real-time autonomous vehicle. The computer people are very imaginative, but not very practical. If they think, well, we can have the cars chain like trains, one follow another. I said, good luck with that. Every car has its own brake response time, okay, and every car has its own acceleration, variation. You want them chain to control, synchronized control. You have a disaster ahead. They're going to be like one hitting another, being too close because they cannot respond that fast, brake that fast, or accelerate that fast. It's the same thing. The human is already doing the best thing on the road. They still got to what, elongated this long when you have a green, red light to green light, right? The human still already has the best response time and still cannot do it. The machine to operate vehicles are all different types. It's a pipe dream. But anyway, so that's the engineering part of things. Theory can be done, but you are all engineers. So once you do something, you really understand the difficulties and the details. Yeah. Can you give me an example of your own experience? On the book, paper is one thing, theory. Once you build it, when you start to build it, then you realize there are so many different factors are never mentioned by paper. Okay. So that, like, what kind of bed do you sleep on? The sleep number bed?
Tempur-Pedic.
Okay. Why do you choose that? Why do you choose that?
It's comfortable.
So I don't really care about bed per se, but my experience with the sleep number bed is that we've been bombarded with TV commercial about sleep number bed, how good it is. So one day I was in the shop in the mall. I really sympathized this salesperson. So okay, I'll try it. And then once I try it, then I had so many different questions. Before I try it, I just totally ignored that. Oh yeah, okay, so it's an air mattress with a different firmness. Call it number. Yeah. That's because everybody has different number, they say. That's on the surface. But once you try it, the OS, you really have so many questions. Like real time, how do you make it real time? The timeline of the time sharing system like what we have is the timer interrupt cycle. So that so this is the CPU time. So CPU will execute instructions, also got interrupted by timer interrupt at 100 Hertz. And then it will execute the timer service after context switching overhead. So there will be a timer service time. Right? You want to keep it small, all the kernel service and time small. And then the rest of the time, the process loader can load the process to run. So you want to keep that big. So this, the rest of the time is for the process. Yeah, until the next time interrupt occurs, this frequency, right? But the process also calls services. When process calls services, it's total asynchronous to timer. So it may happen any moment. Get PID is called the sleep call, the write call can occur. So the process call says write. Yeah. Says write with a very long string, it will take time. Yeah. So what's so funny? Would you share it with us? Not funny. Okay. And then the system write can be executed by CPU passing this point. So you can see the timer interrupt count will be skewed. That's the current OS time count. All right. So there's no guarantee in a time sharing system like this. You can count the real time, like the wall clock. I don't know. Maybe I'm explaining too many things you don't really care. Until I put it on the test. Okay. Give you a hint. All right. So we haven't got to the 650 yet.
Mm-hmm.
So Okay, so this is the coding hints. Okay. And then so you can use the switch statement, interrupt number, and then you can have the service.c switch of the ECS, the service number. And then if it's the get PID service, the answer is here, instar. So the instar can receive the round pin and into the traffic because instar is the EBS address in the traffic. Sleep service, we set the PCB wait time to the current OS time plus 70 seconds. How do you get a 70 second? So the question is, when you program this by description, it's passed over nicely. So if you don't have anything passed over, it will be a problem. How do you get a 70 second? Right? So where do you get it? So that's one potential question. So I say you want to write, I will ask you, how do you write your sleep service code where the void argument passed over? So that's for you to study. I'm not giving out all the answers in the class, okay? But you know what I'm going to ask, okay? So timer service updated with the adding this increment of the current time. That's the OS current time. It's up counted by 1. And then look through the PCB array to look for process, any process, more than 1. It could be more than 1. That the process stays asleep and its wait time is matching the current time. Okay, that means the process needs to wake up and then put into the ready pick queue to be ready to run, to be selected to run. Okay. It may not be selected right away, but it's going to be going back to the ready pick queue. Okay, if not, it's gonna be overtaken as a running process. We could do that. Actually, we could but there could be multiple waking up. So you're going to have a problem like which one is the one that's gonna be the running process. We can only put them into the ready pick queue because they can be multiple. The right service code, like I previously described, the screen display is coded like this. And here you have the VGA pointer initialized to the top left corner. And then we're going to have the flat pan, the standard out display to the target PC console. For every character in the string given, okay. So you see this service code has nicely 3 different arguments given from the call of the service, syscall service. So syscall service needs to extract these 3 arguments given to this subroutine. This subroutine will use them accordingly, so the string can be looped through. And for each character in the string, we're going to give it to what the VGA point to. So that's kind of like your name string. Each character in the name string is this character plus the color mask. And then you increment the VGA pointer. But every time you do that, one character display is done. You want to check the pointer is reaching the bottom right. Okay, the bottom right. The bottom right is from the beginning plus 25 rows. Each row has 80 columns. Okay, so the accumulation of the pointer becomes equal or greater than this. That means it's writing outside or at the end. Then we need to erase the whole screen. To erase the whole screen is a loop as well by setting a VGA pointer back to the upper left and then right blank. Okay, the increment and right blank, yeah? Until this guy, VGA pointer is greater or equal to the bottom right again. Okay, so that is the erasure. It's actually repeat every location right there space. All right, so you can organize your code like this with a slash comment. This is for each. This is its file number. So you don't get lost with parentheses. All right. What do you think? You can do it? Can you do it?
Mm-hmm.
Without looking at the World Wide Web?
No.
Okay. So, yeah, try to do it yourself, okay? And that's really your own ability. Nobody else can take away. You can get hints, but you don't want to get, you want to get as little hint as possible from others. So basically, this is the idea of kernel service calls. Okay. The three services is syswrite, get PID, and sleep. Okay. Other places, you can use console print something, console push something, only when it's the circumstances of the kernel panic. Or as a user, it's the idle proc, or when kernel panic situation occurs. That's only for debugging, basically. Only for the supplemental help from the idle proc. Or any debugging statement, there's a kernel panic to display a message like out of PIDs. Okay, the console put char or console print. We use the console something here. Okay. So that's allowed. Can use this. Or direct access to the VGA display by the idle proc. So basically, we want to limit the user proc using the syswrite service, test the syswrite service. That's kind of like our VGA driver, device driver, even if there's no delay into it right now. Okay, there's no delay into it right now. The following phase 3, we're going to try out mutex at semaphores. Mutex at semaphores. We need semaphores now. Immediately, as you can tell, we have a unique device. In this case, the IO device is the display, the VGA display. If we don't have a semaphore or mutex control, these processes are going to compete, display things onto them. Right now, it doesn't seem to have much conflict until later on. If you change the process to display multiple lines, okay. When you have the process, the user process display multiple lines, by multiple syswrite calls, they can be interrupted, okay, by the timer and cause the preemption because the runtime is reaching the time slice. So user prop 1, user prop 2. We're going to have syswrite, yeah. And then we're going to have syswrite, and then there could be other statements like that. So when you have more copies running the same code like this, they start to compete. And you will have the intermix on the syswrites. So when one process usually, when they occupy the standard out, it needs to exclusively use the standard out without being interrupted. Okay. Otherwise, this one wants to write A, B, C, and then this one wants to write A, B, E, F. Then you will see, the mixture of the writing from syswrite to syswrite. We do have every sys write a string that's exclusively for one process because the kernel going to the write service is not interruptible. Okay, when it serves this writing this string for one process, the string ABC 1, 2, 3 is not interruptible. It's not going to have 1, 2, 3 mixed with 5, 6, 7 the characters, but between is still interruptible, meaning that the time limit can be reached right here. For that process runtime. Okay, and then when it switches this process can be split several times before this restart again. So if this is one document that has several statements to write, okay, because we have a buffer size need to be segmented. The document themselves needs to be segmented, put into the syswrite buffer in portion by portion. So we cannot put out the whole document display on the VGA screen continuously. Just like you send out to print, okay, the whole document needs to be printed on pages continuously before another process can use the printer. So we got to have the mutex in order to control this. So basically, the loop to do printing of multiple lines got to have the process called the semaphore or mutexes to control the occupancy of the I/O started out. Okay. So there will be like a mutex lock of the started out mutex. Okay. And then it loops here to write out the whole document. Okay. And then the mutex unlock the standard out mutex. Okay, this has a the same code, but it will print out its own different document. Okay, maybe by PID, that document file name, all the context, the content is a little different. But you can see, without mutex lock and unlock, they will intermix to print out things between two documents. You know, that's not what we want. So that's why inter-process communication services need to be provided by OS. Okay, Dijkstra has that for Unit 139. He already lists out all the studies. Software want to synchronize among themselves. It's impossible. You got to have the third-party kernel. When the kernel runs, everybody stops. Then the kernel can do the synchronization correctly. Okay? Because these two services are calling the kernel to lock a single unique lock. Okay. And then the kernel locks it, then the process past that point, mutex lock passed, didn't block the process. Inside this region is a critical session, CS, that's the loop. Okay, so this side, inside is called CS, critical session loop. Critical session loop because there's a critical access of the I/O devices or data need to be mutually exclusively accessed by this process only. And this will call the mutex lock. The same mutex that represents the usage is handed out. And this will block. Okay. Block process. This one didn't. Process go into the critical session. Okay. This one doesn't go in. This one will be blocked by the mutex. All right, so there got to be a third party among all of us when we go to the restroom, there must be a kernel waiting there, control this lock. And everyone can request the kernel, say, I want it, I want it, I want it. But we know that counter kernel, there can only be one person. And in that call, INT 128, CPU is executing just one interrupt 128 out of all of you. Depends on which one is the one that CPU is executing. They all come to call 128 almost at the same time. But the first call will get the CPU a kernel's attention to know the run pit is the one that first call interrupt 128 with the surface of mutex lock. And then that process can continue. And then the next process calls mutex lock. Well, the lock is already locked. I already let one person in, so you got to suspend. And then all the other in process runs and suspend, runs and suspend. Because they all call the same mutex want to lock it, but it's already locked by one person. Okay, so then you go in to do your things behind the mutex, do the thing, and then you come out, you call the mutex unlock. Yeah. So the kernel is the service call. You call the kernel to do the mutex unlock. You cannot call yourself to unlock. Okay, why is that? Because it's time here, And once you call mutex unlock, it's another service called 128. You will go to the kernel, suspend the process, actually all processes. And then the next process in the wait queue can continue, go to the ready pit queue and continue to run, meaning that we'll go into the critical session. Okay, and then execute this loop to use the critical IO. Another one is already come out from here. Okay. So it's between application processes themselves. They need to conduct this protocol to use the mutex correctly among themselves or semaphores. It's not that the OS is going to say, hey, you better use semaphore mutex. No, it's the process themselves. Okay, when you design an application, you know there's such a thing called inter-process communication, like semaphore mutex, pipe, signal, file, lock, shared memory management, message queues, and socket programming. Okay, that's the reason. Otherwise, there will be racing condition and complex. Okay. So this can resolve the complex of the I/O. So we're going to do next phase like this. Okay. We can do single lock mutex, multiple locks, semaphores, and then check out the differences. Okay, so you gotta complete phase 2 to understand phase 3. Okay, I cannot wait till you say, oh, you complete phase 2, understood it, then I'm going to talk about phase 3. We don't have time like that. Okay, right now you got to already complete phase 1 in order to do phase 2. Actually, listen to what I said today. Otherwise, you weren't even here. Even though you were here, but you didn't do phase 1, it's a little hard to understand. Okay? You gotta catch up, all right? All right.